Okay. Okay. Good afternoon and namaste, everyone. I'm Dr. Neetu Garg from National Institute of Technology, Kurukshetra, India. And first of all, I would like to thank the organizers for inviting me to this wonderful workshop. And it's an honor to be here. So today I'm going to present on a numerical treatment for a class of multi-term time-fractional advection-diffusion equations. And this work is a joint work with my PhD supervisor, Dr. A.S.V. Ravikant. And the presentation's outline will be, we will start with the introduction and motivation for the problem. And then we will construct the numerical scheme for the problem. And after that, we will be doing the stability and convergence analysis part. Then we are presenting some numerical experiments, and we are giving discussions, and we are also comparing our results with the existing methods. And after that, we will conclude our results. So we will begin with the brief background for fractional calculus, although all of us we know, but we just want to start with the warm-up. So what do we mean by fractional calculus? That is the study of derivatives and integrals of arbitrary order. That order can be any real number or a complex number, that can be a rational number or irrational number. And its origin is found in 1695 when L. Hospital asked Leibniz about the sense of the notation d-half, and Leibniz replied that it is an apparent paradox from which one day useful consequences will be drawn. So, and this fractional derivative operator have the no-local property and possess memory effect. It means that it not only gives us the solution at the present moment, but it also provide us the information at the previous points. So that helps us in the modeling of the complex processes. So that's the reason that we find its wide applications in almost every area of science and engineering, in physics, and viscoelasticity and control theory, diffusion processes, financial problems, and biological problems. So we have so many applications. We have listed here only a few one. And in fractional calculus, when we are working, we have the privilege of choosing any order of derivative. So suppose we have to interpolate some data, and if we are discussing about some subdiffusion problem, so our alpha lying between 0 to 1, so we can choose that alpha which can better describe the dynamics of the problem, of the real life problem. So we have that benefit that we can choose that fractional order. So that's our privilege there. And I just want to mention that how important is the anomalous diffusion phenomena. We have many complex systems like polymers and proteins, and there we find out this anomalous diffusion phenomena, where mean square displacement is not varying with time linearly. There we see a nonlinear relationship. So that is the relationship given here, that mean square displacement is proportional to the time non-linearly. And we know that this gamma, if this gamma lying between 0 to 1, then we call that problems as subdiffusion problems. And if it is greater than 1, then we call it as superdiffusion problems. And it has applications in various fields like nuclear magnetic resonance, bacterial motion, transport in turbulent plasma, and fluctuations in the financial market. Okay, now we have to check means how we can find out the solution for these fractional differential equations. So in general, it's very challenging to find out the analytical solution for the differential equations, fractional differential equations. So that's why the study of numerical methods becomes very important for us. And in literature, there are many methods that are available, like finite difference method, finite element method, and meshless method. And we have listed here a few, that we have so many numerical methods in the literature to solve the fractional differential equations. So in this talk particularly, we are going to focus on the numerical solution of a particular problem. So now let's go to that problem. So we are considering here multi-term time fractional advection diffusion equation with variable coefficients. So because in real life phenomena, we have many complex processes which can't be very well modeled with the single term fractional differential equation. So that's why we have introduced this multi-term time fractional problems, where we don't have only a single term or fractional derivative, just like you can see here. Sorry. Yeah, here you can see here that here we have many fractional derivatives. Here we have m+1 terms, so that's why we are calling that as multi-term time fractional derivatives, because for fractional derivative we have here multi-terms. This next term is a diffusion term, and this is the variable coefficient here. This next one term is the advection term, and this last one is a forcing function. So now this is a PDE, and we have here spatial variable and time variable, and this spatial variable, this lying between 0 to L, and our time is greater than 0. So this is actually initial boundary value problem. So we have with that initial condition as well as boundary condition. So this condition is given here. This is our initial condition where our time is 0. So that is defined to be some function gx, and a boundary condition means our x domain was 0 to L. So when our x is here particularly 0, then that is defined as h1, and here when that is x is L, so that is defined as h2. And here we have different fractional orders, just like gamma 0 to gamma m. So they follow this order, that all the fractional orders lying between 0 to 1. So, and they follow this order. And these coefficients di's are positive constants, and we are assuming that this function e is positive, and we are assuming that all these variable functions, these are sufficiently smooth functions. Okay, now when we did literature survey for this problem, you can see here that we have here multi-term problem. So if here we have a single term, means our I is m is okay, we can take m as 0. So we have there only single term. So that is actually time fractional advection diffusion equation, and that has been studied with the various methods like compact finite difference method, meshless method, and we have so many methods that we have studied this single term problem. But and when in this problem, in multi-term problem, that advection term is missing here. So this is just multi-term time fractional diffusion equation, and that has also been studied by these researchers by finite difference method, finite volume method, and finite element method. And the problem that we are going to study, that was we found only this paper, Hussain et al. They studied that by meshless method, and so we are going to study this problem when we have the diffusion term and we have the multi-term problems. And one thing I forgot to tell you, that here we are using this definition for Caputo derivative, because you know that in literature we have so many definitions, and these one the most utilized one, and most with have interpretation. So we are going to utilize this definition in this talk. So there in literature there are many discretizations for spatial variable. So first we have to, what is our procedure? We are going to discretize our equation in the time direction, then we are going to discretize that in the spatial direction. So for time direction, we have many famous discretizations, just like in the morning, I think Lehel, he explained L1 discretization. So that is very popular one. But the problem is that when we are going to utilize that, so we are not sure that whether we will get unconditional stability or not. Okay, so when we even in integer order problems, when we do Crank-Nicolson kind of schemes, Crank-Nicolson schemes means when we find out this discretization at n+½ time level. So when we follow this procedure, then we get a kind of implicit scheme, and which provide us better stability. So that's the reason that we are going to utilize here Crank-Nicolson discretization for time. And we will be following this discretization given by Karate et al. Because we have here m+1 time fractional derivatives. So for every gamma I, we are writing this discretization where omega i's are given this form and sigma i's are given these values. So these discretization we have to put in our multi-term time fractional advection diffusion problem. So we will get this semi-discretized equation. Okay, and this term here, this is our n+½ is the total truncation error which we get when we are substituting those time fractional derivatives. So that total truncation error here by time discretization, that is less than equal to tau raised to power 2 minus gamma naught. What is tau here? When we are discretizing, we are starting discretizing, so we are doing a partition of x variable and t variable. So tau is the step size in the time direction and h is the step size in the spatial direction. So we can see here that our order of convergence in time direction is 2 minus gamma naught, where gamma naught is the order of the highest fractional derivative. Okay, so we get this order in the time direction. Now, what is our next step? We have this PDE in spatial and in time. Now we have discretized the problem in the time direction. So now further we have to discretize this problem in the spatial direction. So for that we need a method. So let's see, we are going to apply here exponential B-spline method. For that we need exponential B-spline basis functions. So what does that mean? Here basis functions are defined this way. You can see here that this is non-zero value for 4 sub-intervals, and otherwise this is 0. So we can see that these basis functions have compact support. So that is a very powerful property that B-spline functions have. And here these coefficients that we are given here, a bar, b bar, c bar, are given by these values. And this s is the hyperbolic sine ph, and c is the hyperbolic cosine ph, and p is the non-negative tension parameter, which is a very important point in the exponential B-spline functions. Let's see how that is important. Suppose we have to interpolate this data, and you can see these 2 points. So this is our actual curve, and this one is the unwanted oscillation in that. So if you think like a string between these 2 points, and there is unwanted oscillation between these 2 points, and if you put some tension parameter in that, so that unwanted oscillation will be removed. So that is the tension parameter which plays important role in the theory of exponential B-spline functions. And one more thing you should observe, that if I put here too much tension between these 2 points, so that will just behave like a straight line. So that's our point, that this represent a continuum of interpolant ranging from cubic splines to linear spline. So if in the graph there is no tension, so that is just representing our cubic spline, and if we put in the string too much tension, so that will just behave like a linear spline or a straight line. So when we interpolate the data, we have the problem that if our data is supposed monotonically increasing or decreasing, and when we interpolate, that monotonicity may not be preserved. So when we are using exponential B-spline method, so that is the benefit or advantage of these method, that convexity and monotonicity of the data is preserved. In finite difference method, we make a discretization, we make a partition, and we get the solution only at the node points. So this is the benefit here, that we can get the solution at each point of the interval, not only at the node points. In finite element method, we have to find out the quadrature. So here we don't need to find out the quadratures. When we apply exponential B-spline method to a equation, we get a tridiagonal kind of system, which can be easily solved by the famous Thomas algorithm. And these exponential B-splines are utilized in computer-aided designs because of the local nature of the basis function. It means that suppose we are given a data of 100 points, and we make a local alteration, or we change some of the control points. So sometimes our complete graph is changed. So that is the loss that we have to do the complete work again. So this is the benefit of exponential B-spline method, that when we do change in some of the points, so not on the complete graph is not changed. So there is change only in some part of the graph, other graph remains same. So that's why it's very much useful in computer-aided designs. When we do literature survey for exponential B-spline methods, we have seen that this has been utilized for various problems, but most of them were integer order problems, not the fractional one. So that was a motivation, and also because it's a powerful method containing C2 functions. So we wanted to solve this problem by this method. Now, because our functions Bi's are basis functions, so our numerical solution can be written as a linear combination of these basis functions. where these lambda ln, these are unknown functions which we will be calculating further, values of this one. Now, because these are the B-spline functions, so we can find out the value of u at xk, value of u derivative with respect to x, that value at xk, and double derivative of u with respect to x at xk. Now, initially we discretized our problem in one direction, time direction. So we are going to utilize these results given by equation number 8 in the previous equation to get our complete discretized system. So we get this kind of system of equations, and you can check here because k is varying from 0 to m. So we have here m plus 1 equations, but in m plus 3 variables. So we have here lambda minus 1 to lambda m plus 1. So if we want to get a unique solution of the system, so I need 2 more equations. For those 2 more equations, I am going to utilize this discretized boundary condition. So boundary conditions are already given to us, and we are going to discretize those boundary conditions with the help of exponential B-spline functions. So we get these 2 additional conditions, and from here I will eliminate this term lambda minus 1, and from here I will eliminate lambda m plus 1. So finally we will get a system of m plus 1 equations in m plus 1 variables, where the values of this matrix A, lambda n plus 1, and B n are given by these values. Now, when we have to further solve this system, we need to start with the initial value. Just like we do in numerical methods, we need some initial approximation, then we move to the next step. So what we are going to do here, for that, we are going to utilize our initial condition that was given in the statement of the problem. And here we have taken its derivative with respect to x, and we have taken its value at the initial point. Last, we have taken its derivative with respect to x, and we have taken its value at the last point. So we get this system. By solving this system, we can get the value of the unknown at the initial time level, which is lambda naught. So we have these unknowns, lambda naught, lambda 1 up to lambda m. So we get here initial value of those lambda i's, and we can start the iterative process so that we can get the further values of those lambda i's. Now we are going to check, because when we are doing numerical methods, so the most important point is whether our method is stable or not, because if it is unstable, so there is no logic for doing that one. So we have to check that whether the constructed numerical scheme is stable or not. It means that at each time level, if we are getting some error, so that errors are not magnifying. Okay, we want that in balance. So that means the stability part we have to do. So here we used these coefficients in the discretization of the variable, this operator, and means these omega i's are monotonically decreasing and all are positive. This sum of these terms is 1. So I'm just stating these results. And we will prove that the numerical scheme that we just constructed, that is unconditionally stable. Okay. So that thing we have to do. So how we will start that? The last system that we solved, that was given in terms of lambda j's, and we are assuming that lambda j tilde, they are the perturbed solution. So when we take the solution minus the perturbed solution, so we will get our perturbation term. So this is our perturbation term. So in that system, when we put these values, we get these equations. So further, we have to check the stability part. So for that, we will be using the von Neumann stability method, or that is also called Fourier stability analysis method. So that thing we are going to utilize. For utilizing that one, we are going to substitute here delta jk as xik e raised to power iota j phi, where this phi is VH and V is the mode number and Xi is the amplification factor. So we have to check that our Xi means the amplification factor is bounded. If it is bounded, then we can say that our scheme is unconditionally stable, and if it is not bounded, then the scheme is not stable. So we are going to put this value here in this equation number 12. We get a simplified form, this one. Now we are getting this value. We are taking all other term on the other side except this xi k plus 1. Now what we are going to do, we all know what is our principle of mathematical induction. So we are going to follow that approach. We are going to check whether xi1 at the initial point, whether that is bounded. Then we are going to assume that for up to a level. Then we are going to prove that for the next level. So for that here, yes. So here we have taken our value of k as 0. So we get this value xi1 is this capital lambda tilde, and this value is this one. And clearly this value is less than equal to 1. So we get here that mode of xi1 is less than equal to mode of xi0. So this is true for k equal to 0. For applying mathematical induction, we will assume that this is also true for m from 1 to k, and we are going to prove that for m equal to k plus 1. So we started again with this problem here. We get a simplified form, and here we get this form, and all this thing matters on this term. So whether this term inside modulus sign, that is positive or negative. So if this term is positive, so we get mod of xi k plus 1 is less than equal to xi naught. Means we can say that our amplification factor of error is bounded 1, means our scheme is stable. And let's check the other part also. Means if this term is negative, so we get this form, and I want that mod of xi k plus 1 is less than equal to mod of xi naught. So when it will be possible? If we check its value and we get this expression, because here these lambda i's means our fractional orders follow this criteria. So we finally get a result in this form. And here this result, if it is independent of the time step size and spatial step size, so we can say that our scheme is unconditionally stable. So we get that our scheme is here unconditionally stable. And next part is the convergence part, but I will be just stating that one just because of the less time. Okay, so. Okay, thank you. Okay, okay. We can say that numerical scheme for solving this problem has this convergence order. So because it's a partial differential equation, so we can show that it has 2 order in the space direction and 2 minus gamma naught order in the time direction. So this proof I'm just skipping, and let's move to our results directly so that we can just validate our theoretical part, whether that is consistent or not. So here we started with the problem with only single term. Then we will move to 2 term and then 3 term, because we are discussing multi-term problems. So it's better let's start with 1. So we will move to the other problems. Here this is the single term. This is our diffusion term. This is advection term, and this complete one is the forcing function. And initial condition is when means time equal to 0. So this is x square, and x lying between 0 to 1. And for x equal to 0, this is t square, and x is equal to 1, this is 1 plus t square. And this is our exact solution. So let's see our results in the spatial direction. So spatial direction means I have to fix my time step size, and I have to change my spatial step size. So we started with this one, 0.1, and each time at next step, we are just doing its half. 0.1, then again doing its half, then again doing its half. Okay, and P means tension parameter we have taken here 1. So here we are checking results for gamma naught, that is equal to 0.5, gamma naught 0.5, and gamma naught 0.75. You can check that for each fractional order, our spatial order is approximately 2. Even in this case, when gamma naught is 0.25, and here also we get approximate order 2, and here also we get approximate order 2. So that is consistent with the theorem which says that our convergence order is 2 in the spatial direction. Next, we present result in the time direction, and here we fixed our h means spatial step size, And tau means the step size in the time direction. We started with 0.25 and next steps we are just taking its half. And for gamma naught 0.5, you check its order. This is approximately 1.5. For gamma naught 0.7, it is approximately 1.3, and gamma naught 0.9, it is approximately 1.1. So it says that whatever is our fractional order, so whatever is a fractional order, we get our order as 2 minus gamma naught. That we have presented here results for 3 fractional values. You can also check for other values. We have checked that for different values also, but we have presented here only 3, 1. And for whatever gamma naught we are taking, we get order 2 minus gamma naught. Then third table, we present our results, comparisons with the meshless method. And we have taken our results at different time levels. And you can see that clearly our results are better than this meshless method for this case. Now this shows the approximate solution profile. This one shows the approximate solution profile at different time levels. When our time is increasing, our solution profile is getting higher. Also, the straight line is the exact one and approximate is the star one. So you can see that your approximate solution is consistent with the exact solution at every time level. And here we have fixed our gamma naught as 0.5. So first problem, we started with only a single term fractional differential equation. Now let's move to other problem where we have taken here 2 terms of time fractional derivative. And again, we have initial condition and boundary condition and the exact solution. So for first table, we are presenting results in the space. Now, because we have 2 fractional orders, so we have to check values of both of the fractional orders. So here we have fixed our value of gamma 1 and gamma naught we are changing. So for gamma naught 0.5 or gamma naught 0.75 or 0.95, we get approximately order 2 in the spatial direction. And here we present results in the time direction by taking half step sizes. And you can see here we have taken different values of gamma naught and gamma 1. And the theory says that whatever we have the value of gamma naught, suppose it is here 0.6. So we get our order 1.4. So our numerical results are showing that whatever our theory is, that is consistent with our numerical results. So here gamma naught is 0.7. So we get 1.3 approximately order. For gamma naught 0.8, we are getting approximately 1.2. And for gamma naught 0.9, we get this approximately 1.1. So next table shows the comparison results with this method for different values of gamma naught. And you can see here clearly our results are superior with this paper for different values of gamma naught. This is the numerical solution profile. And these again shows the solution profile when the time is increasing, as well as that our approximate solution is consistent with the numerical exact solution. Then in the third example, we have taken here 3 time fractional terms. Just like we started with 2 terms, now we are taking here 3 terms. I think in our paper we have done 4 terms also, so you can check that one. So again, here we have presented our results in the spatial direction to check whether our order is 2 in the spatial direction. And then we presented our results in the time direction for different values of gamma naught, and we have fixed here gamma 1 and gamma naught. For gamma naught 0.6, it is 1.4. So all these results indicate that gamma naught is a fractional order. So our order of convergence is 2 minus gamma naught. These are the comparison results. We are comparing this with the RBF method, and for different values of gamma naught, our results are much superior with this one. And this is the solution profile, and this is the profile when our time is increasing. And this result is published in numerical methods for partial differential equations. So for further example and the convergence part that I skipped, you can look into that paper. And so what we did in this complete talk, we started with multi-term time fractional advection-diffusion equation with variable coefficient. We discretized in the time direction by using Crank-Nicolson approach. We discretize in the spatial direction with exponential B-spline method. So when we get a discretized scheme, then we check that our scheme is stable, unconditionally stable, and convergence of order is 2 in the spatial direction and 2 minus gamma naught in the time direction. We also presented different numerical examples which shows that our theoretical results are correct. And we also presented comparison with the existing method to show that our results are superior. And we can say that exponential B-spline method is an efficient method to solve the multi-term fractional diffusion equations. We have also solved for multi-term diffusion equations. Here we have presented results for multi-term time-fractional advection-diffusion equations. So that's all. These are some references. Thank you for your patience.
Okay.
And I would be happy to answer if you want to ask something.
Is there any question at all or no? No question? Comments? No? Okay, so thank you. Oh, okay.
Okay. Okay. That long time we haven't worked on. We are just taking that nearby time. So maybe I will check with that one and I will discuss with you. Yeah. Okay. Thank you. Thank you
again. So now we have a short break and then we will see again at 3:30.